Somewhere in a lab in California, a machine running at a temperature colder than deep space just did something no computer, classical or otherwise, has ever verifiably done before. It ran a calculation 13,000 times faster than the best supercomputer on Earth could manage, and unlike every previous claim of quantum supremacy that came before it, this one could actually be checked and confirmed by independent observers. Meanwhile, on the other side of the planet, in a German physics lab, two researchers just showed that a 200-year-old law of physics, one taught in every introductory thermodynamics course on the planet, has a loophole nobody knew existed, at least not at the smallest possible scale. Neither of these discoveries involves time travel, neither of them lets a computer become conscious, and neither of them is quite the godlike miracle some corners of the internet are currently claiming. But what actually happened is genuinely remarkable, and untangling the real science from the hype turns out to be one of the more satisfying investigations in recent memory. Let's start with a headline that's actually real and actually verifiable, because it deserves to be understood properly before we get to the parts of this story that don't hold up. In October of 2025, Google's quantum computing team published a paper in the journal Nature describing something they called quantum echoes, run on their superconducting quantum processor named Willow. The algorithm itself is built around a concept called an out-of-time order correlator, a mathematical tool used in physics to study how chaotic quantum systems scramble information over time. Here's the genuinely clever part. The technique works by sending a disturbance through a quantum system, deliberately reversing the system's evolution, almost like running a video backward, and then measuring how that original disturbance echoes back, amplified by the way quantum interference builds on itself. Google's team demonstrated that running this specific calculation on the Willow chip was roughly 13,000 times faster than the best available method on one of the fastest classical supercomputers in the world. What makes this discovery different from previous, more controversial quantum supremacy claims is the word verifiable. Earlier demonstrations of quantum computers outperforming classical computers, including Google's own earlier claims back in 2019, involved tasks specifically designed to be hard for classical computers to simulate, but largely useless for anything else. And in some cases, classical algorithms were later developed that closed much of the supposed gap, reigniting debate about how meaningful the original claims really were. Quantum echoes is different because the result can be independently checked and cross-confirmed using other quantum hardware of comparable quality, and because the underlying technique connects to a genuinely useful real-world application. Working with researchers at the University of California, Berkeley, Google's team used the quantum echoes approach as what they called a molecular ruler, applying it to two actual organic molecules, and comparing the results against real nuclear magnetic resonance data, the same basic technology hospitals use for MRI scans, just applied at the molecular level instead. The quantum-derived measurements matched the laboratory NMR data and, in some cases, revealed additional structural information about atomic distances within the molecules that conventional NMR techniques alone could not easily provide. This matters because nuclear magnetic resonance spectroscopy is already one of the most important tools chemists and pharmaceutical researchers have for understanding molecular structure, used extensively in drug discovery, material science, and the broader effort to understand how molecules are actually shaped and how they interact with each other. A technique that can extend what NMR is capable of measuring, verified against real experimental data rather than purely theoretical simulation, represents exactly the kind of narrowly useful, rigorously confirmed advance that distinguishes genuine scientific progress from speculation. It is not, to be clear, a general-purpose computer revolution. The quantum echoes algorithm is purpose-built for this specific category of problem. It will not break encryption, it will not run a search engine, and it will not, on its own, accelerate every other field of science simultaneously. What it does do is open a specific, verified, scientifically meaningful door, and in a field that has spent years promising breakthroughs that mostly remained theoretical. An actual, independently checkable result like this one is worth taking seriously on its own narrow terms. Now, for the second piece of this story, the one involving an honest-to-goodness rewrite of textbook physics. Though again, the real version is more nuanced and more interesting than the breathless retellings circulating online suggest. In research published around the same period, physicists Eric Lutz and Milton Aguilar at the University of Stuttgart demonstrated theoretically that quantum heat engines, microscopic machines that convert energy into useful work at the scale of individual atoms and particles, can exceed the efficiency limit defined by the Carnot principle, a foundational concept in thermodynamics established in the early 19th century that sets the absolute maximum efficiency any heat engine can achieve when converting heat into mechanical work. Here's the part that gets lost in most retellings of this discovery, and it's the part that actually matters for understanding what's really going on. The Carnot principle, was derived specifically for large macroscopic systems, the steam engines and turbines of the industrial world, where heat behaves according to classical thermodynamics. At the scale of individual atoms and particles, quantum mechanics introduces something classical thermodynamics never accounted for: correlations. Between particles, a distinctly quantum phenomenon with no classical equivalent that can itself be converted into useful work, on top of the energy extracted from heat alone. The Stuttgart researchers showed that a microscopic quantum engine, by tapping into these quantum correlations as an additional resource alongside ordinary heat, can produce more total work than the classical Carnot limit alone would predict, allowing its overall efficiency to exceed the boundary. This is not a violation of the second law of thermodynamics in the deeper sense that something is being created from nothing, or that entropy is somehow decreasing across the system as a whole. Quantum correlations are themselves a genuine physical resource, requiring real energy and real physical setup to establish in the first place, the same way burning fuel requires real energy input in a conventional engine. What the Stuttgart team actually demonstrated is that the classical Carnot framework, built without any concept of quantum correlation, simply leaves an entire category of available physical resource out of its calculation, a resource that only becomes accessible once you're working at a small enough scale for genuine quantum effects to matter. Extending an old law to account for a previously unrecognized resource is a different, more precise kind of discovery than overturning that law entirely, even though headlines describing it as physicists rewriting 2 centuries of physics certainly grab more attention. Both of these stories are genuinely exciting, genuinely real, and genuinely worth knowing about. So where does the godlike discovery framing actually come from, and why should you be skeptical of it? This is where we need to talk about the difference between peer-reviewed research published in journals like Nature, scrutinized by independent experts before publication, and press releases issued directly by companies with a financial interest in generating excitement about their own work. In June of 2026, a company called AIX Global Innovations issued a press release claiming that its proprietary artificial intelligence system had achieved fault-tolerant quantum computing, the long-sought milestone where quantum computers become reliable enough for large-scale, error-free calculations, years ahead of the timeline established by every major, well-resourced quantum computing program in the world. The claim was published through a commercial wire service, not as a peer-reviewed scientific paper, and it was not independently verified by any outside research institution at the time it was issued. Compare that timeline to what the companies actually building large-scale quantum hardware, with billions of dollars and entire research divisions dedicated specifically to this problem, are themselves projecting. IBM, which operates the largest fleet of quantum computers in the world and announced a fresh $10 billion investment in quantum computing in June of 2026, has set its own internal target for delivering the world's first large-scale, fault-tolerant quantum computer at 2029, a date the company describes as an acceleration of previous projections, not a goal already achieved. Multiple other major quantum hardware programs, spanning superconducting, trapped ion, neutral atom, and topological qubit approaches, all describe themselves as making rapid, genuinely impressive progress toward fault tolerance, while consistently stopping short of claiming they've already crossed that finish line. When a single company, working independently of all that broader infrastructure, claims via press release to have already solved a problem the entire, well-funded, heavily scrutinized field still considers years away, that gap between the claim and the surrounding scientific consensus deserves real scrutiny rather than uncritical acceptance, regardless of how confidently the announcement is worded. So what should you actually take away from all of this once you separate the verified science from the marketing language? Quantum computing in 2026 is making real, measurable, independently verifiable progress, just not in the godlike, reality-bending sense some content out there wants you to believe. Google's Quantum Echoes algorithm represents a genuine, peer-reviewed, narrowly useful breakthrough with real applications in chemistry and molecular biology. The Stuttgart thermodynamics research represents a genuine, careful refinement of a 2-century-old physical principle, extending rather than demolishing our understanding of how energy and quantum correlations interact at the smallest scales. Microsoft's ongoing work on topological qubits, including a June 2026 update showing more than 1,000-fold improvement in how long certain quantum states can be maintained, and IBM's enormous continued investment in scaling toward fault tolerance by the end of the decade, both represent steady, well-documented, peer-reviewed progress, rather than a sudden overnight leap to god-tier computational power. The actual story of quantum computing right now is one of patient, incremental, genuinely impressive scientific progress, made by thousands of researchers across dozens of institutions, checked and rechecked through peer review slowly, compounding year over year toward a genuinely transformative technology that is still, by the field's own most optimistic internal estimates, the better part of a decade away from its biggest promised applications. That's a less dramatic headline than a godlike discovery. It also happens to be true, which, in a field this genuinely exciting, turns out to be more than enough. It's worth slowing down on why the verifiability of Google's result actually matters so much to the people working in this field, because outsiders often assume any sufficiently impressive quantum computing claim is automatically trustworthy once a big company's name is attached to it. That assumption has gotten the field burned before. Google's original 2019 quantum supremacy claim, run on an earlier chip, was genuinely exciting at the time, but the specific task it solved was deliberately chosen because it was hard for classical computers to simulate, not because it was useful for anything beyond demonstrating the basic point that quantum hardware could, in principle, outperform classical hardware on some task. Within a couple of years, classical computer scientists had developed improved simulation techniques that substantially closed the gap between the quantum result and what a sufficiently clever classical algorithm could achieve, reigniting a genuine technical debate within the field about how meaningful the original supremacy claim really was. That history is exactly why quantum echoes, being independently verifiable, checkable against real laboratory NMR data, rather than only against theoretical simulation, represents such a meaningful upgrade in how confidently researchers can talk about this result. It isn't just a faster calculation. It's a calculation whose accuracy can be cross-checked against the physical world, which is precisely the kind of evidence that turns an impressive demonstration into a genuinely trusted scientific result. There's also something worth saying about how this single verified breakthrough fits into the much longer arc of quantum computing as a field, because a 13,000 times speed advantage on one narrow algorithm can sound, out of context, like the kind of thing that should immediately transform every industry simultaneously. It won't, and understanding why not is part of understanding the real shape of this technology. Quantum computers are not faster general-purpose computers in the way a new generation of classical chip might be. They are specialized tools, exceptionally good at a narrow category of problems involving quantum mechanical simulation, optimization, and certain types of pattern recognition, while being no better, and often considerably worse, than ordinary computers at the vast majority of everyday computing tasks, from browsing the internet to running a spreadsheet. Quantum Echoes is exciting precisely because it identifies one of the genuinely valuable narrow problems, modeling molecular structure, where this specialized advantage actually translates into real scientific value, rather than being a parlor trick confined to an artificially constructed benchmark. It's also worth being fair to the genuine excitement driving the hype in the first place, because none of this skepticism is meant to suggest the field is somehow disappointing once you look closely. Quite the opposite. Researchers who have spent their careers in this field, including physicists at Harvard's Quantum Initiative who have publicly described the current pace of progress as running well ahead of where they expected to be just a few years ago, are not exaggerating when they describe this as a genuinely thrilling period for quantum science. The difference between that genuine, well-earned excitement and the godlike discovery framing circulating in some corners of the internet isn't the underlying emotion. It's the evidentiary standard. Real researchers describe accelerating, well-documented, peer-reviewed progress toward a known set of milestones, with realistic timelines still measured in years. Press releases describing a finish line that's already been crossed with no independent verification anywhere in sight are telling a different, far less careful kind of story, even when they borrow the same vocabulary of breakthroughs and milestones that legitimate science actually uses. There's a final practical question worth answering before closing this out, because it's the one most people watching a video like this actually want addressed. When will any of this genuinely change daily life? The way the personal computer or the smartphone eventually did? The honest, evidence-based answer, drawn directly from the field's own most credible voices rather than from marketing copy, is not yet, and probably not for several more years, even under optimistic assumptions. IBM's own roadmap, backed by $10 billion of fresh investment and built on the broadest existing quantum hardware fleet in the world, targets large-scale fault tolerance for 2029, not tomorrow. Google's verified breakthrough, however genuinely impressive, applies to a narrow, specialized category of chemistry and materials problems, not to general computing. Microsoft's topological approach is producing real hardware gains, while its core physics claims remain under active scientific debate. None of these honest, carefully hedged timelines is as exciting to read as a headline promising a godlike discovery has already arrived. They also happen to be the timelines coming from the people actually building this technology, rather than from a press release timed to a conference and a stock-friendly headline, which is exactly why they deserve to be the version of this story you actually remember.